There's like one, yeah, right. One off amp, one, or two step, right? I'm using it a lot. Yeah.
Okay, so let's go ahead and begin today. So today we're finally going to talk about the instruction that takes 3 clock cycles to process instead of 2. Remember, prior to today, I've been saying that most real instructions, and again, it's only the real instructions that you have to worry about as far as the microprocessor processing. Okay, because if your processor is processing all the real instructions, then it will do the pseudo instructions, because pseudo instructions are either multiple real instructions, or a lot of times it's a pseudo instruction is a single instruction that just has like a special value or something. Okay, so as I've said before, most of the real instructions take 2 clock cycles to execute the instruction, but there's a particular instruction that takes 3 clock cycles, and we'll see what that instruction is, and also see why it takes 3 instead of 2 clock cycles. So where we're going to start today, you can see I've got the diagram of the otter drawn on the board, and also at each table, I put enough hard copies of the otter diagram, so there's 2 per person. And the reason why it's 2 per person is because we're going to go over the data path and control signals for these 3 instructions. 2 of the 3 instructions are not on Canvas. Okay, this first instruction, it's not on Canvas, so I was thinking you could fill it out as we go along and do it here in class. And same thing with the second instruction. This last instruction here, this is on Canvas, and so that's why I didn't give everybody free. So you can just look on Canvas for this one and just kind of follow what I do here in class, like you've done with the other ones. Okay, so we're going to go through these 3 instructions, and again, eventually you'll see the instruction that takes 3 clock cycles instead of 2, and that's probably going to take the first hour, maybe. Again, it depends on how many questions, but this morning it took about an hour. If it takes an hour, we'll take a little bit of a break, and then after the break, I want to show you a timing diagram for an example program I have. And then the activity today, okay, I sent everybody an email again about an activity for today's class. The activity for today's class is after I go over this timing diagram, I'm going to have you do a timing diagram. And the timing diagram that you're going to do as part of a in-class group activity is the sample program for hardware 6. Okay, so by doing the timing diagram for that sample program for hardware 6, when you look at the simulation timing diagram to see whether your hardware 6 is working or not, you'll have something to go by. Okay, you'll have your reference, which is hopefully correct. All right, so that's sort of the agenda for today. Once we get to the timing diagram, it won't take that long to go over. I know it looks like a lot, but you'll see it's basically what you already know, even though you might not realize it. Okay, but we'll get there. But we're going to start here, like I said, and we're going to come up with the data path and control signals for these 3 instructions, starting with this one right here. So I've got my red for data and my blue for control, just like we've done with other instructions. So again, just like previously when we've done this, it's good to have the instruction manual handy. So if you got your computer, I would bring that up on your computer or your tablet or whatever. I don't think anyone's made a hard copy like I have, but it would be beneficial to you if you're looking at the instruction manual as we're doing it. Okay, so what kind of instruction is this? SW. Yes, it's store word. It's one of the store instructions, right? You have store word, right? Just like you have load word, you have store byte, store half word. They just like load half word and load byte. Okay, so what is this part of the instruction telling us? If you look at your detailed description, right? For every instruction, it has the form of the instruction, right? It tells you if there's a source register, whether it's source register 1 or 2. It tells you whether there's a destination register, tells you whether there's an immediate. Also, in the detailed description, down by where the machine code is, under instruction format, it will tell you the type of immediate, if you do have an immediate. So what can you tell me about this T2 here? What does that represent?
Destination.
Is that the destination?
No, the RS one.
Which one is it?
RS one?
It's a source register RS what? RS2. So this is source register 2, right? Okay, how about in parentheses? What's this? That's source register 1. What's this number in front of the parentheses?
Immediate offset.
Right, that's an immediate. And then what type of immediate does this instruction have?
That's hard.
Right, that's right. Just look under instruction format, right? That's- Okay, now T2, that's an alternative register name for which register. And I also put, I think I put it every table, the page that had, oh, there. Did I put this from the instruction manual? Right? That sheet that tells you which register goes with what alternative name. So T2 is the alternative name for which register? 7. Register 7. And how about S0? That's the alternative name for what one? 8. Okay. Does everybody see where to get this, right? Just look at that sheet. Okay. All right, also, we're told that the contents of T2, which is register 7, is 66 hex, and the contents of S0, which is register 8, is hex 6000. So what does this instruction do? What is this instruction doing? When you write it as part of an assembly language program, what does it accomplish when it gets executed?
It stores the contents of X7 in the first data. Memory or well, this one. Isn't that where data starts?
Well, I mean, there's data, that's true, but like, what is this? We've seen this before, right? You've seen this in load instructions, where there's a number out front of something in parentheses. So what happens here with this number that adds to the bar? Right, it's gonna take this number, add it to what's in this register, and then it uses this as what? An address, right? So it's gonna take the address, after it adds whatever immediate we have to the contents of this register. It's gonna use that as an address and then take the contents of that address and put it in this register. All right, so this gives you the address, and then the contents of that address gets put into that register.
Wait, so the immediate gets added on to the contents of the register, not address of the register?
No, and again, in the instruction, if you read the instruction, it takes this number, it adds it to what's inside that register as 0, but then it uses it as an address. Okay, and then the contents at this address get stored here. So it's the data at this address, after we do the adding, that gets stored in that register. Okay, and again, the reason we know that is if you go and you look here, right, it's going to take the memory at the address formed by sign extending the 12-bit immediate value, adding to the contents of RS1.
I think that's backwards. It says it's like in the example, it stores the value of the first one into the address specified by the second one, and it's offset. like on the,
Where are you reading?
on SW, so like, in this example, it stores the value in X10 at the address specified by X11. And the offset.
Okay, yeah, so X11, which in that example, X11 is where S0 is here. It's adding these two together, then it uses that as an address, and it takes the data, you know, the contents of that address and puts it into this register.
Isn't it the opposite? It's like,
Oh, wait a minute, I'm sorry, I'm thinking of, I'm sorry. I'm thinking of, look, this is, I apologize. I'm reading the instruction right, I'm wrong, you were reading it right. Right, it takes the contents of this register and it's going to put it in the register at this address. So like commonly when we have a store word, you know, we put in, you know, like the address for the 7-segment display or the address for the LEDs here. So I'm sorry. Yeah, you're right. I'm sorry. I didn't replace it earlier, but thank you for being persistent. Okay. Okay. So I'm sorry. Is everybody okay now? Did I confuse everybody or is everybody okay? I'm the only one that was confused. Hopefully you all had it right. Okay. So anyway, now we know what the instruction is doing. Let's see what the data path and the control signals are. So just like last time when we were doing the instruction, where do we start in our diagram with our data path? Yeah, we want to start here at PCL because what is that PCL? Right, the address of the instruction, that's going to be X. So we want to start here. So that address goes to this input address 1 of our memory module. So remember, inside the memory module, that's where we have real memory that's made out of the code segment where the instructions are, the data segment, and the stack. So what do I want to happen here at the memory module?
the names of the DL should have the instructions.
Right, we make the read enable equal to 1, and then at the time of the next 0 to 1 transition of the clock, at that time, the instruction at this address will now be at output DL. So our instruction will be here. Yeah. Okay, then we come back to the red file. And you see, this is where you need to know in your instruction what's RS1 and what's RS2. And you know, RD if we have them. Now we don't have a destination register in this instruction. So since we don't have a destination register, does this input to the reg file matter? Yeah, right, because that's the address if we're going to write to a destination register in the reg file. Right. Okay, address 1, does that matter? Yeah, because we have an RS1. So what is the data going to be on that address 1 input?
S0.
Going to be S0? Because remember, this is just an alternative name. S0 is the alternative name for which register? 8. So it's the 8 that's going to be on the address input, right? Because that's the address of register 8. Remember, the alternative names are just that. They're just alternative names. Okay, so we'll have an 8 here. How about on address 2? That's number 7. Right? P2 is register 7. Okay, does the immediate generator matter for this instruction? Yes. Yeah, right there, it has an immediate, so that matters. And as we said before, it's an S type immediate, so here at the F output of the immediate generator, you're going to have a 0. And then, let's see, what else we have. And then at the output of RS1, we're going to have what?
Contents of it.
Right, contents of X8, which is the same thing as contents of S0. So there we'll have the hex 6000. And then how about at the output of RS1?
Contents of X7 or T2.
Yeah, T2, which is register 7. So that's where the 66 hex is in. Okay? This hex 6,000 is gonna go to this mux here. Let's see this, well, let's forget about that for right now. This S immediate of 0 is gonna go to this mux, and those are the two things that are gonna get added. Right, 'cause again, if you look at the instruction, this immediate, which is 0 in this case, gets added to the contents of your registry, which is the hex 6,000. So the ALU, that's the piece of hardware that does addition. So what do we need to make this control signal here to get this data to the input of the ALU? 0. Right, that's gonna be a 0. Okay, how about this mux here for source B input? That's gonna be 2. That's all right. Okay. All right, so now we have both our hex 6,000 and also our SVM0 at the input of the ALU. So the ALU will add these two inputs provided what? How do we make the ALU add as opposed to some other operation?
The ALU part has to be whatever the addition.
Right, which you can find out on your sheet. Right, but ALU fun, that determines the operation that the ALU is going to perform on the inputs, right? So what does it have to be to add?
So
All zeros, right? 4 zeros. Okay, so that's going to get added. So it's just going to be hex 6,000. Adding hex 6,000 to 0. And that's going to come up like this. And the path is going to be that. And then the path for this instruction for the RS2 data. I'm sorry that these black lines at the top are so crisp. You got the diagram on your bench or even should be able to. So you see what's coming out of RS2 for this instruction, that's going to be the data into to the memory module. And then the output of the ALU, that's going to be address to on the memory module. And now we want to write the data at EM2 at this address. And notice this memory module has a write enable 2. So we would want that to be a 1. Okay? And this is synchronous. This is a synchronous write. In fact, all the writes in the Otter are synchronous. There are no asynchronous writes. And all the reads are asynchronous except for the 2 reads at the register. Okay, so once this becomes a 1, once this write enable 2 becomes a 1, at the time of the next 0 to 1 transition of the clock, the data at DN2 is going to be written to the address of address. So you see that's when this hex 66 would be stored into address hex 6,000. And what's the significance of address hex 6,000?
The first part of the data for the first one.
Right, that's the first word address of our data set. So you see this particular instruction would be writing that data, that 66 hex, into the first word address of the data set. Now, when you do like a store to the 7-segment display or a store to an LED, well, the only difference would be that this address would be an address of an output. So it would be 11000, well, all zeros for switches, right? And what is it? 11. Oh, well, no, we wouldn't have switches because that's an input, but we could have the LEDs 110020 or the 7-segment display 110040. Okay. And then like any of the other instructions we've done where it's not a jumper or branch, we also would have to get it ready for the next instruction, which would be forward an address away from the one that was just executed, right? So what would we want PP source to equal? Zero. Right? And then what would we want PC write to? One. Right, but it's the PC write that will take this address here at PC in and then put it at the output, and then that's the address of the next instruction, which is 4 away from one that was just executed. Okay. So any questions on the data path or the control set? I mean, we didn't miss anything, right? We got everything. Let me double check here just to make sure. Yeah, we got all the control signals. We got, yeah. Okay. Do you have a question?
Why is it not, what is the new address or the memory of the new address not come out of TL2?
Okay, so over here, what's your question now? Why doesn't what come out of here?
I'm thinking of T into, why would it not come out of TL2?
Because we're storing instead of like reading.
Okay.
Yeah, you're gonna see when we get to a load instruction that EL2 matters. But here we're storing to an address, so we're writing to an
We're
address.
storing it, we're not storing it in the register.
Well, we're storing whatever's at this address. And the address here is 6,000 hex, which that's the first word address of your data set. You know, again, if this was a store to like the LEDs, then this address would be the address for the LEDs, 11000020. Remember in the previous problems, am I getting that right? Yeah, it's 11 and 4 zeros and 20. The 7th segment is 11, 4 zeros, 40. So you know, if you're writing to the 7th segment display, then this address would be the address for the 7th segment display. Yeah, you'll see where DL2 comes into play when we get to the load instruction. Okay. But yeah, for a write, we don't care about, or for a store, we don't care about DL2.
There's like signals, so is it one, when it takes the address one, the other one, and then the rest of it is like happening in parallel, so the second is just storing on the third would be PC.
Yeah, we're gonna get to the details of like the timing, but just real quick, you're basically right that it's one clock cycle to get the instruction at the output DL1. That's one clock cycle. That's what we call fetch. You know, we're getting the instruction. Then it's one more clock cycle for most instructions except for the one we're going to get to. Okay. For most instructions, there's a second clock cycle for when the instruction appears at the output of DL1 through everything else, through, you know, writing this to address hex 6000, also getting the address for the next instruction to be executed. All that is in the execute cycle. Okay, so yeah, most instructions take the 2 and basically it's get the instruction, make the instruction happen. It's the 2 cycles. Yeah. Any other questions before I erase? Because I'm going to erase what we have before we do the next instruction. We did this one. Okay, everybody's okay if I erase what I have up here? Okay, so if I miss something, let me know. I'll try to get all of it. This. All that. This. This. Try not to erase too much black here. Fire rate something again. You got the diagram on your hand. All good. Did I miss anything over there? Did I get it all? If you see something I missed, let me know. I think I got it all. Did I miss the blue numbers? Does that look good? Okay. All right, so let's look at the next instruction, this AUIPC. So what does this instruction do?
It's the data. It's the data of the immediate value and the current value of the PC and adds them up
Okay, close. There's one.
and stores them into the destination register.
Okay, and then also it's shifting, right? It's shifting 12 bits. It's called an add upper immediate to PC. So you're right. Everything you said was right. But then also there's the shifting of the 12 bits of the immediate before it gets added to the PC. There was another instruction that we did talk about previous to today that also did that shifting of 12 bits. And it also has upper immediate in it. In fact, I think it was the very first instruction we ever did a data path in control signal for. You don't remember? LUI? Oh, my screen went blank, but there's an LUI in that example program that when we get to the program, or when we get to the timing diagram, we'll look at. But yeah, the LUI, that's a load upper immediate. Okay, so it also has that shifting of 12 bits. Okay, but this one here, it's going to shift the immediate by 12 bits, add it to the current PC, and then store that into a destination register. Now, I don't think I've ever seen this instruction as like a single instruction, but this instruction, if you look at the load immediate instruction, which is a pseudo instruction, the load immediate instruction is made out of this along with, well, it's LUI, I think, along with the add-I, something like that. So it's some sort of combination of this. Okay, but anyway, let's just look at this here. So now for this example, we're going to assume that the program counter is at 24. So it's at an address of 24. I just picked that number out of the air, but this number has to be divisible by what? 4. Yeah, remember that our instructions are all separated by 4 in address, right? So any output of the program counter, it's got to be divisible by 4. Okay, so I just picked that number that's divisible by 4 out of the house. Okay, so what do we have here? What is T1?
RD.
Right, that's a destination register for this instruction. So that's RD. And T1 is the alternative name for which register?
6.
Next 6. Okay, what's 80? Immediate. And then what type of immediate is this? It's a U type. Okay, so now we're ready to go ahead and do our data path control signal. So again, we start here at the output of the program counter. What do we want to happen here at the memory module? Right, this is the address of the instruction. What do we have to do to make the instruction here at the output? Right, you need read enable to be 1. So then at the time of the next rising edge of the clock, that's when our instruction will be at the output, EL1. Okay, so what matters here at the reg file for this instruction? This, yeah, just WA. Address 1, address 2 doesn't matter, right? Because we don't have an RS1 or RS2 for this instruction. So just WA matters. And what's the data that's going to be at WA? It's going to be a 6. We're going to write some register 6. Hey, immediate generator matters because we have an immediate. And it's a U type. So the U output matters. And it's going to be B. Okay, what else matters here? Because what are we going to add that immediate to?
Yeah.
Right, we're going to add it to the current PC, right? The current instruction address. So that's over here. Right? You can see how this connects. Okay, this connects to input 3 of this month. And what does adding? What's the only module that does the adding operation? ALU. Adding, provided this is what?
Yeah.
All zeros. Okay, what do we want ALU source A to be? A 1. That will connect our immediate of 80 to source A input of the ALU. What do we want ALU source B to be? What is it? 3. Right, do we want the PC output, the other input of our ALU? Now those two get added together. So what data are we going to have at the output of the ALU? Because we got 80 and this would be 24, right? We'll have 104. And then that 104, right? The addition of the PC and our immediate is going to be put into a destination register, right? So what do we need RFWR select to be? What does this select have to be? 3, right? Because we want to take this and store it into a reg file register, so this has to be 3. That puts it at the input WD, and then for the write to actually happen, we need what? We've seen this before because we've written things to a reg file register before, right? So what does this have to be? The 1. And then when the next, after this becomes a 1, the next 0 to 1 transition of the clock, that's when the data actually will be put in the destination register, in this case, register 6. A question?
So our instruction has 80 in it, but the U type coming out of it is also 80, so was it not shifted at all?
Say that again now? What about this 80?
AUIPC, we said shifts the immediate 12 to go back.
Oh, okay. I think, and correct me if I'm wrong, but I think what your question is getting to is where that 12-bit shift happens.
Or what effect did it have? It happens in the immediate generator, but
Right, yeah, in fact, let me write that. And in fact, what other instruction did that happen? Because we saw this before today, right? We talked about this, but, you make that 12-bit shift happen when you design the immediate generator, right? If you look at the, what is it, the U-type immediate, you can see that there's 12 zeros, right? Your 12 least significant bits are all made to be 0, which just shifts the data 12 bits to the left. That happens for the LUI command too, right? The load upper immediate. And so the 12-bit shift that happens here. So,
then our instruction had 80, and it's outdated, so.
Well,
what
Re-
effect-
remember, well, it goes back to how this immediate generator is designed. This immediate generator is taking these 25 bits and then arranging them as specified in the, the format for that type of immediate. And it shifted to 12 bits. So the way that these bits are put together, right, these 25 come in and then we put them together in a certain way, make a 32-bit, which is that immediate. I mean, as long as for that type of immediate was pieced together correctly with these 25 bits, you're gonna get this right number up. And it's gonna be shifted by 12 bits. So, I mean, that's all happening here. I mean, what's coming in here is just the 25 bits from that machine code instruction. But what's being spit out, again, if the format is followed, is the correct immediate value. I don't know if I'm answering your question or not. Is that what you're getting at, or? Is it
So as
something?
a programmer, we don't have to worry about that shift, it's just in the hardware, we build chips.
Right, this was done in the hardware, yeah.
But the 80 that we put into the instruction is what we're going to be added, 80 is for the instruction.
Right, this 80 is what's coming out of the immediate generator that gets added to PC. Yeah. And again, it's being taken care of how this is designed here. This is what's creating. Okay. All right, so any other questions on that diagram? I don't think we've missed any. Oh, we didn't finish over here. We gotta finish to get it ready for the next instruction. So again, this is gonna be just like before, since we're not branching or jumping. Right, if you're not branching or jumping, this is gonna be 0. And then you always need your PC write to be a 1. So you'll advance to the next address, the next instruction to be executed. So yeah, don't forget about that. That's important. Okay, but no other questions before I erase what's here? Okay, everybody's okay if I erase this? All right. Okay. So we're gonna get to the load instruction. That's where it gets interesting. Not that this wasn't interesting. It gets more interesting. So this. Erase this. You hear about all the cold weather that's coming? It's supposed to get down like in the 40s. They said it may snow on West of Great. Did I get everything? Do you see any red or blue? Well, there's little reds. Do you see any blues? I think I get everything. All right, so. Did this one. All right, so now this one's on Canvas, so that's why I didn't give you 3 of these sheets, because this third one's on Canvas. All right, so what kind of command do we have, or instruction do we have here? LW. Load word. Okay, this is what I was saying about the store word that was wrong a little while ago. I had load word on. All right, so what is T0? If you look at the form of the instruction, what is that telling us? X5. Okay, X5, that's the non-alternative name, but is that a source register, destination register, or what is it? Yeah, that's the destination register. What is S0?
RS1.
RS1. Then S0 is the alternative name for which register? X8. And then 0 is a immediate. And what type of immediate do we have for load instructions? I type. Okay, so what's this instruction gonna do? You remember what I said earlier, incorrectly for the store instruction. It's correct for the load instruction. So what does the load instruction do?
It's the contents of, uh, whatever address I say in the immediate create, and then places it in X5.
Right, so it's gonna add this immediate to whatever's in this register and then use it as an address and then put the content of that address into this destination register, right? Just the opposite of what a store does. Okay, does that make sense? Okay, so let's see what the data path is. So again, we start here at the output of the PC program counter, right? Because that's where the address of the instructions be executed is at. So what do we want to happen here again? It enabled 1, but then at the next 0 to 1 transition of the clock, we'll have our instruction at the output of the L1 of the memory module. So what matters at the reg file? Does RS1 matter? Or address 1 matter? Right, we have an RS1, so what's the data gonna be there? 8. Does address 2 matter? No, because we don't have an RS2, but we have a destination register. So WA matters, and what's going to be the data at WA? 5. Okay, we have an immediate, so the immediate generator is involved here, and it's an I type. Now, this is an error, a typo that's on Canvas. On Canvas, I incorrectly have that the immediate's an S type instead of an I type, but I did correct it. Like you look on Canvas at the very top, it has important correction, immediate should be I type, not S type. So I just wanted to point that out. Just so you don't miss it if you look at this on Canvas. So yeah, the I type is the immediate, so 0 here. So RS1. Okay, now I didn't put contents of this register 8, but you know, I didn't give like a specific data or number, but we can just put just write like contents. Contents RS1, and that's gonna go to see this monk's over here. And then let's see what else we have. Yeah, so what do we want this ALU source A to be? We want that to be 0. And then what do we want ALU source B to be? We want that to be 1. So we'll have this immediate at the input, 1 input of the ALU will have contents of RS1, or excuse me, contents of register 8 at the other input of the ALU. So then we want the ALU to add these 2, correct? Right, we want to add those 2, and then we're going to use it as an address. So what do we need ALU fun to be to add? All 0s. Okay, so here we're going to have 0 plus whatever the contents of S0, which is register 8. And we're going to use that as an address. That's gonna go over to. This address two of the memory module. And you see, this is where the problem lies. Okay, because remember, we want to take the data at that address and put it into our destination registry, right? Which is register 5. And all, our destination register is here at the reg file. But do you see what the problem is? Because here, we have synchronous reads and writes. And are we doing a reading or a writing here? The load command. We're doing a read, right? Remember when we did the store, we were writing to this address. But you see here, we're doing a load. So we're reading from this address 2. So we would want this read enabled 2 to be a 1. But you see, the problem is that this read is synchronous and also this write is synchronous. So, see, this is where a third clock pulse comes into play, because if we only have 2 clock pulses on the rising edge of that second clock edge, TL2 hasn't updated yet to that new data at this address. It still has the old, whatever data was there before. So you see, with the load instruction, you need an extra clock pulse. You need an extra state. Otherwise, you're not going to get the correct data to your destination register. It's going to be the data before the data you want to be written to that destination register. Does that make sense? Okay, so I kind of summarized what I just said. This is kind of the concise way of saying it. That the problem is that the data at TL2 changes to the data at address 2 on the next rising edge of the clock, which is the same clock edge that the data at TL2 is supposed to be saved. All right, so if you have a load instruction with just 2 clock cycles, the proper data is not going to be stored in the destination. That's the bottom line. Okay, we need an extra clock edge or clock cycle. And that means in your state diagram, we need another state. And that third state, third clock cycle is only for load instructions. Okay, if you look back at all the other instructions, we never had a case like this. We never had a case where we were taking the output of this memory module and then putting in a destination register. The load instructions are the only instructions that have this peculiarity. So you see, the solution to this is to add a third state. Okay, so add third state. And we call it the write back state. And again, it's only for load instruction. All right, so like load word, load byte, load half word, and also the unsigned version. Now, load upper immediate, we did that previous to today, and load upper immediate only needs 2 clock cycles. Okay, because if you look at the data path of the load upper immediate, it doesn't even involve this. Okay, so when we say load instructions, we're talking about those. Okay, load upper immediate is not included here. That's a 2-cycle instruction. Okay, so where the write back state would go in your state diagram is right here. And you would only want to go to this state if you're doing a load instruction. Okay, if you're not doing a load instruction, then when you're executing, if you're not executing a load instruction, you just go back to the fetch, right? But if you're doing a load instruction, you go to write back, and then after the write back state, you go back to fetch. Okay, so if it's not a load instruction, you're just still doing this. Like if you had a program like your hardware 6 program doesn't have load word or load byte or load half word. It has an LUI, but again, LUI 2 clock cycles. Right, so like in your sample program for hardware 6, it's just doing this. It's just 2 cycles for every instruction. Okay, but when you get to your final project will have to work for all instructions. So you'll need a write back for your final project. Now, the other thing to keep in mind, and let's finish this here, right? Because we also have to get ready for the next instruction. Now think about this. For a load instruction, which we see needs 3 states now, right? Because it takes 3 clock cycles. When I'm in the execute state of a load instruction, right? So when I'm right here, what do I want PC write to? When I'm in the execute state of a load instruction, do I want it to be 1 like it is for all other instructions? Now, why don't I want this to be a 1 for a load instruction when I'm in the execute state?
You don't want it to be a bunch there.
Right, you don't want to move on to the next instruction until the load instruction is complete, and the load instruction doesn't complete until write back. Okay, so when you're in execute for a load instruction, you know, like make a little note somewhere, you know, for a load instruction, here you would want PC write to be 0. It's not until you get to the write back that you would want PC write to go to 1, because then the load instruction's been executed, so then you advance to the next instruction. Does that make sense? So, you know, to finish this, you know, during the write back, we get our DOut 2 data, and then we want our select to be 0. Data and WD. Then you would make your ready for equal. So that would happen during the write back.
So what is the DOut2 data?
What is the DOut2 data if we don't have a 3rd state for the load? Is that what you're saying?
Do.
Oh, if you do, then it's gonna be the data at this address. Yeah, so this is what I was incorrectly saying, you know, when you were all, you know, getting this right, and I was getting it wrong, right? Is, you know, think about when you use the load word or a load half word in your programs, right? That's when you're getting data from switches. So if this is the switch address, the data for the switches would be a DOut2, provided you had that 3rd write back state. If you don't have the 3rd write back state, well, then at DOut2, we don't know what it's going to be. It's going to be whatever that was before, you know, which could be anything. Okay, so any questions about this? Because this is what we were working to. You know, when I was getting ready for this class, you know, last couple of days, you know, when I was thinking about it, I was kind of debating to myself. I was like, well, you know, it's been a while since we've done these diagrams, you know, it's been like a week or so. And I was debating, should I just jump into the load instruction, like start with the load word right away? But then I thought, well, let me show you a couple that we haven't talked about that don't require a 3rd state. So you could hopefully, you know, get more back into the groove, so to speak, as opposed to just jumping into something new, like see something that's familiar, right? Because these 2 instructions, even though you haven't seen those instructions, the diagrams are fairly familiar. Okay, so hopefully by doing that, you see what the difference is. You know, why this requires an extra state, an extra clock edge. Okay, so why don't we, at this point, why don't we take a 5-minute break? So 10 past, and when you come back, we'll step through a timing diagram of an example program. And then after that, I'll have you do the activity, which will be the sample program for hardware 6. And what you're gonna see is these diagrams, right, with the data path and the control signals, they're not only important for when you actually design your control units, right? When you write the Verilog code for your control unit FSM and your control unit decoder. These diagrams are also important to understand the timing diagrams. And it's the timing diagrams that you use to verify that your otter is working. Right? When you have your otter all together and you generate the mem file for that sample program that we have for you with those 6 instructions, and you go to sim it on Vivado. Well, what tells you whether it's working the way it should is the timing diagram. So I'm actually going to have you do the timing diagram for that sample program, so you'll know ahead of time what it should look like when you go to sim it on Vivado. Okay, so that's the goal of the remaining class here. Okay, so yeah, let's take a break till 10 past and we'll start up again. Oh, thank you. Actually, Paul, right? Yeah. Paul pointed out an error I made. This E out 2, it goes to input 2 of the month, not 0. This here, I erased the line, but this goes somewhere else. Oh, this 0 goes to, oh, it goes over here. See how I erased this line? I did that last class because it was getting too cluttered. So this actually goes over here. So this should be a 2, not a 0. So thank you very much for correcting on my part. Okay, so that should be a 2. Thank you. That's very important, right? Because if you have the incorrect control signal for any instruction, the instruction is not going to work. So thank you. Thank you. Yeah.